to reach a distant star. So I'm going to start here with the Earth. There's the sun, and I'll put the Earth right here. This is our solar system. We'll have a distant star over here somewhere, and we're going to say the distance between the Earth and the distant star is about 10 light years. That is as measured in the Earth's frame of reference. So here, this is as measured from Earth. And then we're going to have a spaceship, and the spaceship is going to travel to the distant star at some unknown speed, and the crew will measure a time of 2 years. So that will be as measured from the ship. So we've got 2 frames of reference. One will be the Earth, and I will designate that as a distance d and a time t. The other will be from the ship, which I will designate as a distance d prime and a time t prime. So prime on something means it's relative to the ship. Without one means it's relative to the Earth. Now I want to find out how big v is. Well, v's are always found by measuring distances and dividing them by times. What we have to be careful about is that the distance and the time have to be in the same frame of reference. So I could use them as measured from the Earth. I can also use them as measured from the ship. However, the problem I have is I have the distance as measured from the Earth, but the time as measured from the ship. So I don't have basically the top and the bottom of either fraction to calculate the speed. I cannot take the 10 light years and divide it by the 2 years because that's the distance measured from the Earth and the time is measured from the ship. Not only that, if I tried it, I'd end up getting 5 light years per year, 10 divided by 2, and that would tell me I have to travel faster than the speed of light, and Albert Einstein would not like that. So what we need to do is figure out how do I get the distance as measured from the ship given the distance as measured from the Earth. Those two are connected by the time dilation. Now, in order to use that, I have to figure out which one of those is the proper distance. So we'll redraw the diagram and see if I can figure out which one of these, I'll use black, so I'll use black again. Which one of those is the proper distance? So there's the Earth, here's my distant star. Now, what I can imagine doing is taking a gigantic meter stick, putting one end at the Earth, the other end at the star, measuring a distance of 10 light years, and this is a meter stick. That is at rest relative to the Earth, ignoring the relatively small orbital speed of the Earth compared to our rather gigantic speeds going to distant stars. Because I'm using a single meter stick that is at rest with respect to the 2 objects I am measuring, I can measure those 2 distances simultaneously, and that defines the proper time, the proper distance. So therefore, the distance as measured from the Earth is the proper distance. So I'll put a sub-zero on there. That means proper, which then means the distance as measured from the spaceship is the contracted or non-proper distance. So that tells me that d prime, distance as measured from the ship, will equal the distance as measured from the Earth, which is the proper distance, times the square root of 1 minus v squared over c squared. That means, now that I know this is 10 light years, I use the length contraction formula to get the distance as measured from the ship. Now I can go back and look at my velocity equation, which gave me the velocity is the distance as measured by the ship divided by the time as measured from the ship. But now I have that related to the distance as measured from the Earth, my 10 light years, times the square root of 1 minus v squared over c squared. And all of that as measured, the time as measured from the Earth. Excuse me, the time as measured from the ship. Now I have to ask, which one of these times is the proper time? So let's consider the problem again. And again, we've got the Earth here. And we've got our distant star over here. We're going to draw our spaceship. And here's our little spaceship. We can imagine putting a clock on the spaceship and ask, what time, well, that's the time that measures 2 years, is that actually measuring? Well, it's going to measure the time between two events. Event number 1 is when we depart. We can imagine that clock on that ship recording the time the instant they depart. Then that ship can then travel all the way over to the distant star and measure event number 2, which is the arrival. That arrival can be measured using the exact same clock as the departure. So I am measuring this time interval. This time is measured using one clock in the ship frame of reference. That defines the proper time. So therefore, my time, t prime, equal to 2 years, is the proper time. So we put a sub-zero on that, which means I can then put a sub-zero on that, and I am now just about ready to solve the problem. As I know, the expression has v equals a known distance divided by a known time times the square root of 1 minus my unknown velocity squared divided by c squared. And c again, I know. So now we're set to write down the equation that we're going to solve. We have v equals v0 divided by t0 prime times the square root of 1 minus v squared over c squared, but c is equal to 1 light year per year. That makes it convenient because my distance is in light years, 10 light years, and my time is in years, namely it is 2 years. So if I put my speed in the same units as my distance as my time, I can now be a little sloppy and ignore units because they're all the same. So I can rewrite this now just substituting in numerical values. So v equals 10 divided by 2, which is 5, times the square root of 1 minus v squared over c squared, but c is 1, so that's just v squared. Here is my equation to solve. And I have to solve that for v, which is conveniently the only unknown. To do that, we have to square both sides of the equation. That means v squared equals, this entire side has to be squared, so that's basically 5 squared, or 25, times the square root of 1 minus v squared squared, which is just 1 minus v squared. Collecting terms together, first distribute this, that's 25 minus 25 v squared. I have to take this v squared right here and bring it to the other side of the equation, so I'm going to end up with v squared plus 25 v squared, which is 26 v squared, equals, the only thing left over there is the 25. Then we divide both sides by 26, equals 25 over 26. And then we take the square root, so v equals the square root of 25 divided by 26, which is about 0.98. That is my speed, 0.98. So that means the required velocity of the spaceship is 0.98, and that would be in light years per year. If a ship travels at that speed, it will cover 10 light years as measured from the Earth, and 2 years as measured by the ship. The reason it does that is the distance the ship travels is actually not 10 light years. As far as they're concerned, they traveled a total of 2 years, at a speed of 0.98 light years per year, which means they traveled a little bit less than 2 light years. They actually traveled 1.96 light years in the 2 years. So as a result, they don't think they actually traveled that far because their distance they traveled was contracted compared to what the Earth thinks the distance was. But the Earth thought the trip took a long time because as far as the Earth is concerned, they traveled a total of 10 light years at a speed of 0.98 light years per year. So they're going to claim the trip actually took closer to 10 years. Or actually 10.2 years. So Earth thinks the trip took 10.2 years, traveling a total of 10 light years. The ship thinks they only traveled 1.96 light years, and it only took them 2 years. They will disagree on the distances, they will disagree on the times, they will agree on their common relative velocity.